All right, so welcome back, everyone. We'll continue with the second talk of Doron Puder's mini course.
Okay, thanks. Good morning. Okay, so yesterday in my first talk, I gave the introduction to the questions that I'm going to partially answer in this mini course, and we gave some motivation, but eventually we go to the point where I ended last time with presenting these results. Okay, and remember we have two setups. One is a free group, which relates to graphs, and one is surface groups, which relates to surfaces. And so you remember, we eventually what we have is random permutations. Okay, we fix an element in one of these groups, and we map the entire group to the symmetric group via a uniformly random homomorphism, and we look at the image of a particular element, and this gives us a random permutation, or we can sometimes call it a gamma random permutation. Okay, and this is of course in the symmetric group Sn, and we can do it for every n. And then I presented these two theorems that tell you something about the expected value of the number of fixed points of this random permutation. Okay, so my goal today is, and today's the second topic of the mini course is the argument for the free group and why surface groups is harder. So gamma 2 is harder. Okay, so this should take me about, I think, about half of the time of this talk, and then we'll go to start talking about representation theory. Okay, so yeah, so let's start with this. So I want to show you the argument for these results of Nika, and we'll do it by an example. So let's fix. Let's take gamma to be the commutator in F2. And I want to count fixed points, right? So the way I do it is let's say that, assume that so I is a fixed point. Of gamma. Okay, so let's look at the trajectory of I. Let's look at the entire trajectory of I through this permutation. So, so this is the permutation A, this is permutation B, A inverse and B inverse. And remember that here we compose permutations from left to right. So I start here with I. So this is I. And then I end, this is a fixed point, so I have to end with I. And then here I have some other indices. And they're all, so all of them, I, J, K, and L are all numbers between 1 and n. And what I'm going to do is to count fixed points by, I'm going to divide all the possible fixed points of gamma by the trajectory, namely, by whether or not these four indices are the same or not, okay? So all I care about is whether they're the same or not, and then we get several cases. So, so as you can see, I like tables. We have a lot of tables in this talk. Okay, so let's so the first case is when I, J, K, and L are all distinct. So I'm going to draw it as there is an associated graph. So as a graph, I'm going to denote it by keeping these four vertices. So this is a graph which corresponds to this trajectory of the fixed point, and the four edges, the four vertices are distinct. Okay, and this graph also comes from, if you remember the way we thought about a random cover, how it corresponds to a given pair of permutation, we said that we look at, we have the numbers 1, 2, up to n, and then we have one permutation A. Okay, and the second permutation is B. Okay, this is B. This is the cover corresponding to the particular homomorphism. And when we have, actually, when I say that this case, when I, J, K, and L are distinct, it corresponds to finding this graph embedded here. Okay, so I get a fixed point of this commutator with four distinct elements in the trajectory, if and only if I get an embedding of this graph in the covering space. Okay, I mean, in the covering space, it should look like, so you have four different points. Let's say this is the first point, you have some A going here, and then some B going here, and then an A inverse, and then a B inverse. Okay, so this is an embedding of this graph here, and it gives us a point of this case of the commutator. Okay, and now let's see what is the contribution of this case to the expected valid number of fixed points. Okay, so how do we do that? Okay, perhaps I should. Okay, so first I want to choose the four different indices, I, J, K, and L. So how many possibilities do I have for that? Okay, I have n possibilities for I. Okay, let's do it. Okay, let me do it here. So I want to what is the number of possibilities of I, J, K, and L. And then times, I want to carry the computation here, and then I'll just put the results in the table. So what is the number of what such that they are distinct? Times the probability that now I have I have A and B random permutations. What do I want? I want, this is I, J, K, and L. I want A to take I to J and L to K, right? So I is mapped by A to J, L is mapped by A to K, and the same with B. J is mapped by B to K, and I is mapped by B to L. Right? So I want these two conditions. This is the contribution. And well, this number is just n times n minus 1, n minus 2, n minus 3. This is the way to choose four different distinct elements from a set of size n. And this probability, and so now I'm going to use first the fact that A and B are independent, right? I can choose them independently. Now A is a permutation where I have, I know that I is mapped to J and L is mapped to K. So how many ways do I have to complete this permutation? So I have n minus 2 factorial permutations that map I to J and L to K, and this is out of n factorial. And the same for B, right? I have two constraints. Okay, and so overall I get, let me copy the result here. So I get n times n minus 1, n minus 2, n minus 3, and in the denominator I get n times n minus 1, n times n minus 1. Okay, this is the first case. The second case, so let's assume that we have this graph. Now this is A. This is B. Now here I is the same as J and L is the same as K, but they are different from each other. So this is the case where I is J, different from K, which is the same as L. And by the same argument, so first I choose the vertices. I need to choose the value of I and the value of L. And now A is a random permutation, is a uniformly random permutation with two constraints. So the probability that a random permutation satisfies these two constraints is 1 over n times n minus 1. And B, this time has only one constraint. It must map I to L, and that's it. So this is 1 over n, or n minus 1 factorial over n factorial. Okay, and let's give one more example. Let's take this graph. So now this is A inverse, B inverse. This is now I and K, and this is J and L, and so now I equals K. Okay, so by the same reasoning, here I have n times n minus 1 possibilities to choose the values of the indices, and every permutation has two constraints. So I get this. Okay, and overall we have 4 more cases. There are 7 cases overall for this example, but there's nothing special about this example. We always have finitely many cases. For every word we choose, we have finitely many cases. For each case, we get a rational expression, which is a contribution, and therefore, overall, we get a rational expression, okay? So this proves this second part of, this proves this second result, okay? We get a rational expression for every, I mean, if you sum up, here, if you sum up everything, all the 7 cases, in this example, you will get 1 plus 1 over n minus 1 for this particular word, okay? And why does it only work for n large enough? Because, well, obviously because some of these cases cannot hold for a small n, okay? You need n to be large enough, so you can choose, for example, 4 different vertices. Or you need these formulas to not have a pole. Okay. Okay, so this is the argument for B. What's the argument for A? So the argument for A, now we need to understand the limits. Okay, we need to understand what happens when n tends to infinity to these arguments. So let's look again at what these arguments, what these expressions tell us. So in this expression, notice what is the degree of the numerator? So the degree of the numerator is always, we have n to the, we have 1 factor for every vertex. Okay, so the degree of, this is roughly n to the number of vertices. And the denominator, we get 1 factor for every edge. Every edge corresponds to a constraint. So this is AV minus E. So the leading term of every expression is actually n to the V minus E, which is the Euler characteristic of the graph. Okay, and this is true for every such graph. So here we get just n to the 0. Here we get n to the minus 1. This is n to the minus 2. And so on. We always get n to the Euler characteristic of the graph. So what is the leading term? What happens when we take n to infinity? We are only left with those where the Euler characteristic is 0. Okay, and which graphs have Euler characteristic 0? Connected graphs? Yeah, only cycles and okay, you could have cycle and trees, but basically you can, it's not hard to show that. Right, and by the way, we cannot get a positive Euler characteristic because this is a tree, and we look at words that are not the identity, so we cannot get a tree, so the Euler characteristic is always non-positive, and it's, so it's 0, so actually the limit, we see that the limit is just the number of, sorry?
You don't have leaves, so you can't have.
Right. Yeah, unless my word is not reduced and not cyclically reduced, and then I have I start with a leaf. This could happen, but so we say that the limit this tends to the number of cycles of cycle graphs. Okay, and my claim is that the number of cycle graphs, I'm claiming that this is equal to the number of divisors of Q. And why? Because if you have a cycle, remember these all cycles have the word, my word is always a closed path in this cycle. So a closed path in this cycle can only be if the cycle is a root, corresponds to a root of my word. So for example, if Q is, sorry, if gamma is gamma naught to the Q, to the 6, then the possible cycles are, you have the hexagon with gamma naught in each one of them. You have a triangle. You have a bigon. And you have, okay, these are the possible cycles in this analysis, okay? So this is the proof of Nika's results. So I should say Nika's result is a bit more general, but this is basically what you need to know to prove. I mean, I didn't tell you all of the whole result of Nika, but this is basically what you need to know. Okay, any questions about that? Okay, so so we proved that this result for free groups. So now I want to see what happens. What happens if we try to do the same for surface group, for gamma 2. Okay, so first of all, if we try to do the same to carry out, we can still take the same word. This word also we can think of it as an element here. And we can try to do the same analysis. But there is one, what's the first problem? Where does this analysis breaks for surface groups? Yeah, okay, so, right, so, I mean, yeah, this part is the problem. First of all, yeah, A and B are not independent anymore, right? We take 2 random permutations, but they have to satisfy some constraint. I mean, they're actually, so we know that the product of commutators is 1. So it has some effect on the commutator of A and B. And secondly, I mean, in general, it's not that easy. I mean, this part of the computation is not that easy. It's not clear what is the probability that A and B satisfy these constraints, okay? So this is the hard part. Okay, but perhaps what you could believe, and this is actually what we believed for a short while, perhaps these formulas, we cannot exactly compute them, but perhaps this is still, the leading term is still the right, perhaps we get some different formulas or different functions, but perhaps the leading term is still the right thing to look at. Perhaps it is still the Euler characteristic of the graph. So let's look at some yeah, okay, so let's look at some examples. Okay. So I don't want to take exactly these graphs. I want to take some particular other graphs, but in general, I mean, in this problem, we look at various words, okay? So I'm not going to talk about these graphs. I'm going to present some other graphs which show you where we see problems. So let's look at I want to look at the graph. And I want to understand what is the expected value of so the contribution, or let's say the expected value of the number of embeddings in a random n cover. Okay, this is just another way to say the contribution to the expected number of fixed points. Remember that this is equivalent to the number of embeddings in the cover. So let's look at three graphs. First, let's look at this graph A. Let's look at the graph. Let's take the octagon with A, B, A inverse, B inverse, C, D, C inverse, D inverse, and let's take the bouquet with four petals. Okay, so what is the expected number of embeddings of this graph? So this is, okay, this is actually exactly the number of fixed points of the element A, right? Every fixed point A is just one letter. Every fixed point of A would look like that in the cover or in general. The trajectory, this is the trajectory of a fixed point of A. So this is the same as the number of fixed points of the generator A. Okay, these are now A, B, and C, D are now the generators of my surface group. And this, okay, we didn't prove it, but I said yesterday that this has some asymptotic expansion. So this is 1 plus 1 over n squared plus 2 over n cubed. Okay, I didn't tell you where it comes from, but this is true. So let's see what is the, so the leading term. Okay, leading term and other characteristic of the graph. So the leading term here is n to the 0, and the other characteristic of the graph is 0. Okay, so okay, this still works. Now let's look at this example. How many times do I see this octagon in the cover? So remember that how do you construct the covers? We took n such octagons and we glue them together. So we don't always get such an octagon because occasionally we can glue, for example, if we glue, for example, this A to this A, then this is not embedded anymore in the cover. But, okay, but you could guess, and it is true, that in most time, usually these octagons are embedded, okay? If you take and I mean, we proved it, it's not clear, but intuitively it should be right that this should be roughly n to the 1, okay? Roughly all octagons would look like that, or almost all octagons would be embedded eventually. We don't glue an octagon to itself. Right, yeah, thanks. Okay, so let me just, so this is, okay, this is theta. So theta means that this is up to a constant, this function, up to a, up to a constant, this should be the answer. And here the leading term is n to the 1. But what is the Euler characteristic? Yeah, it is still 0, okay? This is just a cycle. Okay, good. This would be my next point. Good. What about this guy? Okay, what's the other characteristic? Yeah, one vertex, 4 edges. Okay, so minus 3. But let's see, what is the number of what is the number we see here? So actually, you see, I mean, I can put here any point. This is I have here. I can choose the point here. Let's say between 1 to n, where it is exactly embedded, or so I have n possibilities for which point, which element between 1 to n to put here. And then I know that all the A, B, C, D, all 4 permutations fix this point. This means that the rest of the points are just any homomorphism to Sn minus 1. Okay, so the probability that I see such a picture with points, let's say n, is exactly the number of homomorphisms from gamma 2 to Sn minus 1. This is the number of possibilities to complete this to a homomorphism from gamma 2 to Sn. And because I just want probability, I'm dividing by the total number of homomorphisms. Okay, and this is roughly, so remember I stated this result yesterday. This is roughly gamma 2. This is roughly, okay, in the limits, this number is 2 times the size of Sn minus 1. Cubed. And this is twice Sn cubed. And what I get here, so this is n over n cubed, so this is 1 over n squared. Okay, so this is n to the minus 2. Okay, and you see that, again, so I have this problem. So the leading term doesn't behave like, yeah. Okay, so let me. Okay, so I want to understand what is the number of embeddings. Okay, so I'm saying this is the same as the number of, this is n times the probability that the point, this is now the point n, the element n is mapped by A to itself, and also by B, and also by C. Okay, by symmetry, okay? Because this can happen in either, like, it can happen in each of the elements 1 to n, and it just, so I have n times the probability that this happens for the element n, and I'm saying that, okay, so just and this, so this the probability that all this that n is fixed by all the elements is just the number of ways to complete these 4 permutations to a homomorphism, and this is exactly the number of homomorphisms from gamma 2 to Sn minus 1, because everything else is like independent, and this is over the total number of homomorphisms. Okay, and then by what I said we said last time about the size of this, we get that this is roughly 1 over n cubed, and together with the n, we get 1 over n squared. Okay. Okay, so we have a problem. We have 2 problems. One is that we do not know how to compute this for now, and the second thing is that we don't know what the leading term is. So how do we make sense of it? So there are actually 2 ways to make sense of it, and the first one is what Mahan suggested. So what Mahan said is that, okay, this, for example, if we take the octagon, it has all the characteristic 0, but whenever it is embedded in the cover, we actually also have the octagon, the face, the two-dimensional octagon inside, right? Okay, so how do we make sense of it? So one way is, okay, so whenever we see this guy embedded, we actually see the full octagon embedded. And the Euler characteristic of this guy, so this has Euler characteristic 0, but this already has Euler characteristic 1. And this already behaves well with what we wrote before. What about whenever we see this? What do we actually see? What happens to the octagon? Yeah, it's just one octagon glued. This is actually a disguise for. We actually see a surface. So this actually represents in the cover we have a small connector component which is just identical to the surface. So here again, this Euler characteristic is -3, but this Euler characteristic is -2, and again, this is already behaves well with what we saw before. Okay, but this solution, I mean, there's a problem. We can't always. This is not the general case. I mean, I can't give you examples. This is not we don't always can just put in octagons and fill the picture and get the right Euler characteristic, because sometimes we don't see. In both these cases, we actually have a boundary of the graph contains a boundary of a full octagon. This is not a general case, but what we do get, and this is how I will say it vaguely. So what we will see. So the general thing is that instead of graphs, we consider pieces of surfaces which are made of vertices, edges, and octagons. So the full octagon, I mean the two faces, and we try to evaluate the expected number of embeddings of such creatures, and every such creature is always embedded in some. Sometimes it is one-dimensional, but in fact it is always embedded in a cover. It can always be embedded in an cover if it is a. And when it is embedded, we can fatten it. I mean, this kind of, so even if I take, for example, so this is, okay, so generally piece of surfaces, you take, so we have this model of octagon, we have covers made of octagons. So what we can take is just a finite subcomplex of this. So pieces is just a finite subcomplex of an actual cover. But it always originates in some cover, in an actual cover, which is a surface. So even if we have one-dimensional, but not all of them are embedded in the universal cover. Some of them are embedded. So this guy is not embedded in the universal cover. Each one of them is embedded in some cover. So they're all embedded in some cover, not necessarily universal cover. And we try to, and since they're always embedded inside surfaces, we can take an absolute neighborhood of them. We can make them a bit fatter. So for example, you can imagine we have something like that. So we have here an octagon. And perhaps there is an edge and the loop, okay? Okay, this is, for example, a piece that could happen. I mean, it comes with some labeling. So there's some labeling. This is a legitimate piece, but it's always embedded in a surface, so we can fatten it a bit. I mean, this is already fat. But now we can assume that this is now some kind of a fat graph. And now it has boundary, right? And what we show, and so I'm going to state it vaguely that if the piece has nice or short boundary, then the expected number of embeddings of this piece is theta of n of the Euler characteristic of, okay, let's call it, if the piece y, the Euler characteristic of y. Okay, and what is, so I need to tell you what nice is. So nice means basically, roughly that this boundary doesn't contain any a segment which is more than half of an octagon. So you can basically, so for example, if I have, so this, imagine this has a, in the covering where this piece, let's take this piece. And in the covering, these 5 edges are part of the boundary of an octagon. So in the covering, what I can do is I can add this octagon. And then what happens to the boundary? Instead of having, I replaced 4 pieces of the boundary. Sorry, 5 pieces of the boundary with 3 pieces. So I could shorten. So I could have made this piece with a shorter boundary. Okay, so this can be made into a precise statement. I don't want to. We'll only get to this in the 4th lecture, what the details are. But yeah. So it's not exactly small cancellation. This is not the only case. You can also have, this is more if you know the work of Bierman and series, they show exactly when, they tell you when a word let's say in this presentation in the presentation we have for the surface group, you're given a word when it is the shortest representative of let's say conjugacy class, yeah. So it's not only that. So there you look for not only more than half of the relation. You also need you also have some other. You could also have, for example, such scenario. Okay, so these are 2 octagons. See, I mean. So you see, you have 2 octagons. You just have a half of an octagon and another half, but you can shorten it. If you go to the complement, you only get, this is shorter, right? Instead of having length 8, now you have length 6. So you have these 2 conditions, but the way we get to it, we don't go, I mean, this is the very magical part of this work, is that We get to these conditions from representation theory. We recover these conditions that appear in the work of, well, of some of it appears already in the work of Dan, and some of it in Bierman series work. But in our case, we recover them from representation theory. Okay, so all of this, and we'll give more details in the fourth talk, all of this comes from, this is one way to make sense of it, but there's a second way to make sense of it. To make sense of, of the, so we had this problem where this didn't match the Euler characteristic of the graph, that doesn't match the Euler characteristic, the leading term doesn't match the Euler characteristic of the graph. But there's another way to fix this problem, and it's not, and this is, and I'm glad that Nir already talked about Euler characteristics. So the second way to make sense of it is to, instead of considering the Euler characteristic of the graph, we consider the Euler characteristic of the subgroup that it corresponds to. Okay, so the second way, for a piece, again, for a piece Y, okay, so we have a piece Y. Remember, this is a subcomplex of a cover. So we have so Y is embedded in some cover of X, of some cover of X, and we can consider the subgroup corresponding to Y, so we call it phi1 labeled of Y. This is just the image of the fundamental group of Y in our gamma 2, in the surface group. This is a subgroup of gamma 2. Okay, and then the theorem is that this is now for any graph or any piece, that the expected number of embeddings is actually roughly n to the Euler characteristic, not of Y, but of this group, the group that it represents. So the Euler characteristic of the group okay, and again, so Nir talked about it a bit, of this group that Y represents. Okay. Yeah, exactly. Yeah, so yeah, I'll give examples, but notice that in our case, so again, we didn't exactly define what is the Euler characteristic of a group, but again, in our case, we have only two possibilities for what kind of group we have. This is always a subgroup of the surface group. What are the subgroups of surface groups? They are always either free or a surface group. So and the only thing you need to know is what Nir already mentioned, that the Euler characteristic of a free group is 1 minus the rank, and the Euler characteristic of a surface group of genus G surface is by definition the Euler characteristic of the surface, which is 2 minus 2G. Okay, this, by the way, you can also, this you should think about it as the Euler characteristic of the bouquet with K loops. Okay, so let's look at the examples we had. Sorry. Okay, so let's look at that. What is the Euler? What is okay, I'll continue this table to the other side. What is the labeled pi1 of y of this piece? And what is the Euler characteristic? So I call it labeled by pi1 because it's not pi, we fix the point and then we look at the path at the I mean we can fix the point and then look at the closed path, but also we read the labels and we think of them as elements of the group. Okay, so what is the pi1 lab here? What is the group that this corresponds to when we project it to the surface? Okay, the only thing we see is powers of A. So this is just A. And this is, the group is Z, and the other characteristic is 0. Okay? What do we see here? What is the image of this group? So this is just a cycle, right? And this cycle reads the commutator of AB and then the commutator of C and D. What is it? What element is it in the group? It's a trivial element, okay? So this gives us the trivial group. And the other characteristic of the trivial group is 1. Okay? And notice that this agrees well with this one. And here, what is the image of this group? Yeah, this is the entire, I mean, we get here, this contains all the generators, so we get the entire group. So the other characteristic, this is gamma 2, and the other characteristic of gamma 2 is 2 minus 4, right? So it's minus 2. So this also works. And this works in general. But I should say that this is something that we learned, we understood only after even writing this paper. I mean, this is the real work is this theorem and boundaries and stuff. But then afterwards we realized that we can get also this yeah. So the real work is here, and we realized afterwards that this is also true. But to prove it, we use the first theorem. What? And so it means that it doesn't have. Okay, one way to say it is that. Okay, if it doesn't have a nice boundary, it means that whenever in every embedding of this piece in a cover, you can shorten the boundary by adding octagons in every embedding, and this translates to the fact that it's equivalent to saying that you don't have in the boundary, you don't have such pieces of either. This is called a long block, so more than half of an octagon at the boundary, or a chain of octagons where together they form this kind of. So you have two possibilities, basically. Okay, any questions about that? Okay, so I think I'll just tell you some open problems, and I will start the representation theory tomorrow because yeah, because yeah, I won't be able to prove 20 minutes. That's enough to prove the first thing that I wanted to prove in representation theory. I think 1, 2. Yeah, it won't be enough. Okay, so yeah, so I will not get into representation theory today. I'll start it tomorrow. So instead, I'll talk about some open problems that are. Okay, so I want to say that in this right, so there are two main open problems. One is about what happens for other groups. So I mean, I still want to keep Sn, but I want to change F2 or gamma 2. So of course I said, I mean, F2 is actually representative of all three groups. And gamma 2 is, what I said is true for any orientable surface group of orientable surface of genus at least 2. And okay, so I should say that this is known. So we have similar results for three products of finite groups. So for example, you can think about PSO2Z, which is free product of C2 and C3, and there are some other Fuchsian groups of this type. So we have similar results, but with some twists, and I don't think I'll yes, completely, yeah. So for example, if I pass, so right, I mean, the F2 is a finite index subgroup here, but if I look at the asymptotics here, because I mean, actually the answer, the asymptotics come from Euler characteristics of subgroups. And here, because I have torsion elements, I get Euler characteristics which are not integers. So when you take the asymptotic expansion in this case, you will see not just powers of n, but fractional powers of n. So you get which are fractional powers of n. So it will be like n to the 6, n to the 0, n to the -6, and so on. You get a asymptotic expansion with this kind of powers in this case. Yeah, but it's still open for. But what about? Oh, by the way, okay, I don't want to get into it, but okay. So this is known, but we don't know anything else, any other group. So, for example, even the case of gamma 1, which is the pi1 of a torus. Okay, so this theory, at least some of it breaks. I think it will be clearer tomorrow when we talk about representation theory. You'll see that. Okay, perhaps. Let me remind you. I told you yesterday that even the set, this number of homomorphism from gamma 2 to Sn, we said that this is a Sn cubed times the sum of Euler. We go over all irreducible representations. And we take 1 over the dimension squared. But when we take Z2 instead of gamma 2, this becomes 0. So you see it's Sn cubed times this is just the number of irreducible representations, which is the number of partitions of n. So this doesn't converge anymore, and this represents a bigger problem. I mean, things do not converge well. Yeah, so it's not clear here what happens if we take. I mean, I think it should be. My guess is that there should be some asymptotics with powers of root of n, but I'm not sure about it. Okay, what about unorientable surface groups? So my guess is that things should behave the same, but we didn't work it out yet. Okay, and you can also think more generally about rags or about, okay, you can just take your favorite group and, or perhaps, the manifolds groups. I mean, I should say that there are some groups where obviously this kind of phenomenon cannot, so let's say I'm using this theorem. Roughly, this theorem holds in all the cases that we know, okay, so far. So this theorem holds also in the free group. If you think about it for a second, in the free group, there is no difference between the order characteristic of the graph and the order characteristic of the subgroup that it represents. These are the same thing, because this is always an immersion. An immersion of graphs, the pi1 is always embedded. So in the free group, it holds in surface groups, and it also holds here in these finite groups. So if you want this theorem to hold, then you have some conditions on what are the possible Euler characteristics of subgroups. So there are some cases where you know it cannot hold, but in these cases, potentially it can, and we just don't know whether it holds or not. Okay, so there is this family of open problems. Okay, so what other open problem is, okay, so from our theorem, so let's go back to surface groups. So remember that if, we said that if gamma is a non-power, then the limit of the number of fixed points goes to 1. Okay, but as I said, I think I mentioned it yesterday, if we want to improve, for example, the 316 result to something better, we need to understand not just the leading term, but what happens afterwards. What is the error term? So the question is, what is the what's the leading, or what is the next term? The next non-zero term. Okay, so so we have this asymptotic expansion. Okay, so it should be some power of n, some negative power of n. So where does it come from? So we do have. So let me give you a. So remember, we speak with examples. So we had we talked about the fixed point of A, and we said that this is 1 plus 1 over n squared. Okay, so so I'm talking about this term, and for the commutator in the surface group, I told you yesterday that this is 1 plus 2 over n plus something, and I'm talking about this term. So what is this term? Where does it come from? And we have a conjecture here. So the conjecture goes as follows. Okay, so let's denote by gamma. Okay, I don't. Yeah, let's call it. Okay, let's just call it F. Okay, F of gamma is going to be. I want to take a look at all the subgroups. I want to look at all the subgroups of the surface groups that contain gamma, such that gamma is not a free factor. Of H. Okay, so, okay, we said, I mean, what does this mean? So what can H be? So H, remember, H is a subgroup of a surface group, so it's either a free or a surface group. If it's a free group, then we just said that gamma is not a basis element of this free group. And if it's a surface group, what do we say here? Nothing, okay? Because a surface group doesn't have, a surface group is one-ended, it has no free splittings. So gamma can never be, it doesn't have any proper free factors, okay? So for surface groups, this always holds. For free group, this is a meaningful condition. And we want to take the Euler characteristic of this group, and we take the maximum value. So the maximal Euler characteristic. And okay, this is not a conjecture, this is definition. Okay, and the conjecture is that the expected number of fixed points of gamma minus 1 is the leading term is n to the Euler to this f. And here the coefficient is the number of these critical edges, critical subgroup. Okay, so this definition is a number, but it depends on the existence of some special subgroups. And one can show that the number of such subgroups is always finite. I mean, groups of maximal Euler characteristic which contain gamma not as a free factor. And if this conjecture holds, I mean, the conjecture says that this is the coefficient. Okay, so let's look at, so does it work? Okay, obviously it works in the example, otherwise I wouldn't have written the examples and the conjecture together. So let's look, this number, the element A. So now I'm looking for subgroups of the fundament of the subgroups of gamma 2 where A is not a free factor. So what kind of subgroups can I take? Yeah, so, okay, so. Right, so, okay, so it's not clear. Okay, I should say I'm not sure about it, but I'm pretty sure. Okay, so I'm not completely sure, I'm pretty sure. Right, good, yeah. Okay, so you know what, yeah, let's start with this example. So now I have the commutator. So the commutator of A and B belongs to the subgroup generated by A and B. This is a free group on two generators, and this one is not a primitive element. It's not a basis element. It's not a free factor. So this one is a critical subgroup. And the Euler characteristic of F2 is -1. Okay, so this corresponds to, this shows us that this is at least -1. And it cannot be 0. Why can't it be 0? Because, okay, perhaps, okay. Wait, before that. Okay, when is F0? Zero means that gamma is contained in a cyclic group, a copy of Z, but it's not a free factor. Okay, but the whole group is a free factor of itself. Okay, so this means that gamma doesn't generate the group. Okay, so this means that gamma is an element, is a non-generator of a cyclic group, which means that gamma is a proper power. Okay, and we know that we get here that the leading, this is of order 1. This is the first theorem I stated, right? that the expected number of fixed point is more than one. It's the number of divisors of if it's a proper power, we get here the number of divisors. So this should be of order 1. And this agrees with the theorem that I mentioned, the first theorem. Okay? For proper powers, this error term is of order 1, of order n to the 0. Okay, and yeah, like I said before, this commutator is a non-primitive element in this group, and that's why we also have a 1 over n, the error term. But why do we have here 2? So this 2 means that we should expect another group, another F2, where this is not primitive. Yeah, okay, this is also non-primitive in CD, right? Because this is the same as the commutator of CD minus 1. So it's here. Okay, and so this explains this example. And if we want A, so now I want to talk about this example. So I'm pretty sure, even though I didn't write down a proof, that a single letter is going to be primitive in every free group. So you have to look, the only groups where it is not a free factor are the surface groups. And what is the surface group of highest order characteristic? What is the surface group, the subgroup with the highest order characteristic? Okay, it's the group itself, the whole group. So A is contained in gamma 2 as a non-primitive element, as not as a free factor, and the order characteristic of gamma 2 is, like we said, minus 2, and this explains this 1 over n squared. Okay, so okay, the fact we believe this conjecture because this is true for free groups. Okay, this is a theorem for free groups. So you should and knowing that it is true for free groups, and you look at these examples, it's very compelling to conjecture it for surface groups. And yeah. So so this is a result of my self-imposed system. Okay, so I think yeah. Okay, so it's a good point to end, and tomorrow I will start talking about representation theory.